Definitely could have gotten from the right.
I really like the circuit. I'm sorry. I think I will. But right now it's
Good morning. Is that working? That's working. Okay. You're stuck with me today. Can you believe it? I hope it's going to be interesting. And Wes is going to pray for me because I need it.
Dear Holy Father, we're grateful for this day, this time we have to be here with Dr. Snelgrove. We're grateful for all his research and scholarship that's led him to this point. We ask thy spirit to be upon him and bless him as he seeks to teach, that he'll have the spirit to guide him and be able to share the message that he's prepared in the way that he hopes to, that we will have our minds enlightened to hear his word and understand it. We're grateful for all the works of thy hands that give us this beautiful kingdom of thine. We say these things in the name of thy son, Jesus Christ. Amen.
Amen.
I think Wes is giving me far more credit than I deserve. So. Yes, that's it. Just a little disclaimer. I don't actually have a doctorate degree. You can call me whatever you want to. But yeah, okay. And that's okay. I chose not to have one of those. This is my friend Scam Likely calling me every morning. He seems to call me. I don't know what's going on. This is important to you, right? If you have any questions, talk to somebody who knows. I don't know anything about it. So thank you for letting me come and do this. I've been interested in physics, of course, for 45 years and longer before I even knew what physics was. And about 10 years ago, I got really excited about nuclear stuff, maybe a little longer ago. I'm really into energy policy and why energy matters to us. And we get told a lot of crazy stories. And I'm very pro-nuclear energy. So I got researching it and discovering that there's a lot of bad information out there. Let's put it that way. Okay. And so I spent the last 10 or 15 years of my personal time just trying to learn something about nuclear. And I'm going to try and share with you a few things. We got 3 days. It's not much. Hopefully the slides and the videos that I've suggested to you will help give you some things to think about. I really strongly encourage you to keep learning. Okay. There's no way I can teach you everything you need to know in such a short period of time. And of course, I'm not smart enough to know what you need. So I'll just take a best guess here. Okay, so now I got to learn how to operate his machine. That? Okay, so there's the official reading assignment you're supposed to have for today. Hopefully you got a chance to do that. By the way, I have a YouTube channel for BYU physics demonstrations, and I've curated a whole bunch of videos for 106 as well as other topics. If you find you want to supplement your understanding with some other videos, they're not as entertaining as Dr. Francis, but I didn't make them, so I don't have to take any credit. Okay, so there's our YouTube channel there, playlist. Okay, and this is what I'd like you to get prepared for next Thursday. Is there a pointer in this?
No, there was separate.
That's the pointer.
Yeah.
Okay, I know how to run this. I just don't know how to run yours. This lady's talk right here, for those of you who are going into something related to life science, she's amazing. She's super smart. It's a long video. I encourage you to watch it just simply because it's going to be good for your education, right? And she dispels a lot of the myths that are out there. Okay. Oh, I'm sorry, I not actually watched this thing myself. This is probably preparing presentations. You see what you see, and now I'm seeing for what you see for the first time. Okay, so how would you like to solve some of these problems? Reduce pollution, reduce some poverty, have less carbon monoxide, sorry, not carbon monoxide, carbon dioxide, improve medical outcomes, fight cancer, improve food safety, understand Earth's past, and so much more. How are you going to do that? Okay, obviously trying to be prophetic here, you're going to do that by nuclear science. And there's just a huge number of things that are out there. We're going to try and talk on the third day about some of those things. Okay, here's an outline of some of the things that we're going to try and talk about over the next 3 sections that we talk about. I'm not going to read those, of course, but this is what I'm going to try and talk about today. Hopefully we'll get through it. Okay, so we got a little quiz here. You guys ready for your quiz? You're going to have to teach me how to do a quiz. That's one of the disadvantages of not teaching classes here at BYU, is that I don't know how to run all of these little tricks. Oh, that sounds like a lot. Okay. All right, did we get a chance to answer there? Oh, still clicking away. All right, is that about it? This is a similar, so that's A again. That was it. Right? Okay, what do you think here? Oh, that must be in different order. Sorry. Then I hit B to show you what you think you knew. Okay, you think C is the right answer. Why do you think C is the right answer there? And what do I do next? B again. B again. Okay. This is a common misconception that somehow, so yeah, we're looking at it's natural and man-made, but that somehow this is an insurmountable problem, something that's more complicated than we know how to deal with. And that's what I'm hoping to dispel with what we talk about. Okay, what is this thing we're going to call ionizing radiation? Okay, and the answer is really simple. Many of you have had chemistry before. You've heard the term ion, right? It simply means that you were able to strip away some of the electrons from the atom. That's what an ion is. So any kind of radiation that could strip away electrons is ionizing radiation. Okay, it's that simple. What's the source of ionizing radiation? Well, there's lots of sources, and we're going to talk about a little bit of those. Not all of them are nuclear, and so let's not confuse that. What was the first ionizing radiation discovered is what we now call X-rays, 1895. And this is a really fun picture. This is Röntgen. I'm butchering that German name, but that's okay. For those who speak German, this is actually a picture that one of the early pictures that he created of his wife's finger using X-rays, and there's her wedding ring. Okay. And of course, we're quite familiar now with X-rays as a technology. So I won't spend too much time, but that is ionizing radiation. Okay, I can do this. Too many buttons. Okay, the thing we're going to spend quite a bit about is what were originally referred to as Becquerel rays. Becquerel is this man on the left here, and 2 of his colleagues, which are probably perhaps more famous than him, are these 2 folks right here. You know who this amazing woman is right here? Yeah, Marie Curie. Although, and I always feel sad that poor Pierre got killed in a vehicle accident when he was fairly young, and Marie had to carry on her own because the team was great. They were amazing, and they had a daughter who and her husband ended up being Nobel Prize winning physicist as well. So incredible family story. I don't want to tell you too many things about it. These guys were dealing with uranium ore and tons and tons and tons of uranium ore, thing called pitch blende. out in their backyard, basically. Big, huge pile, trying to do this. Of course, Marie's claim to fame was that she was an amazing chemist, right? And one of the few people that actually won 2 Nobel Prizes, right? One for chemistry, one for physics. Her husband actually was a well-renowned physicist before he met Marie, and had several very important bits of physics that he discovered. But anyway, he literally was the reason why she was able to be successful, because he supported her, right? It was in a day when she on her own would have had a bit of a difficult time. He also was a great man in the sense that he refused to accept the Nobel Prize unless all 3 of them got to share it equally, which was amazing. Okay. And a fun story about Marie during World War I. She's a widow by then, unfortunately, and she recognizes how terrible the carnage is of the war, and she sets up out of her own pocket a fleet of mobile X-ray vans going out on the battlefield, taking X-rays, helping people, with their surgical things. So an amazing person in all kinds of ways, and I love history, and I hope that you like to look at some of the cool things that have happened in the past, so we can learn from them. Okay, here's a fun little video. Let's see if I know how to make this work. I think I know how to make this work. Okay. This is just a little clip. This is what's called a cloud chamber. These little traces here are just ionizing radiation, and they're natural. There's nothing in that chamber that's causing these things. These are just things that are happening around us all the time, and we don't even know them. Prior to 1896, nobody ever knew that literally tens of thousands of these events were happening. You sitting in your chair have about 13,000 muons zipping through your head every second, and you didn't know it. Okay, you have no way of detecting it, and they don't do you any harm. And so, okay, I got to figure out how to get back. How do we get back? Get back to the. There was some sort of song about that. Get back to where you is. Is that it? There we have 2 things over there. Okay, so here we go. So lots of fun. This is called a cloud chamber. It's a fun visual thing. Scientifically, it was very important in helping us discover radiation's effects. But now it's mostly a novelty. Okay, so where do we get ionizing radiation from? There's actually 2 sources. There's atomic interactions, which some of you are already quite familiar with if you've had some chemistry. And then there's nuclear interactions, both of which can produce ionizing radiation. Okay, ultraviolet you're very familiar with. Okay, X-rays you're very familiar with. Those are considered atomic interactions in that they have to do with the atomic structure. Okay, not the nuclear structure. And so in physics we talk about those being not nuclear. They're still ionizing radiation, but we refer to them because their origin is what the electrons are doing. That make sense? And in the case of nuclear, these are things that are happening in the nuclear interactions. We'll talk a lot about these. We have gamma rays, not on that one. Okay, we have alpha rays, beta, and neutrons. We're going to talk a lot more about these things. And then gamma rays, which are electromagnetic. But physicists define a gamma ray basically as if its origin is from the nucleus, and if its origin is from the electrons, then it's an X-ray. Some people don't always use that definition. Okay, but don't worry about it too much. Okay, how many of you have heard of alpha, beta, and gamma before? Oh, good. I'm going home. Okay. I love this picture because not everybody is as intelligent as you think they ought to be. Okay. Where does ionizing radiation come from? Obviously, we have UV. That's probably the one you're most exposed to. The one I wanted to point out to you is a class of materials known as naturally occurring radioactive materials, or norms. And those are things like uranium, thorium, and actually the potassium in your body. And so we're going to use this little detector here called a Geiger counter. We're going to put a naturally occurring radioactive material in front of it. It's a rock. Okay. Now, the rock has a lot of uranium in it, but it's a rock, okay? You can literally go out and hike across the deserts of Utah and find these things, okay? They're all over the place, a rock. Here's an example of another naturally occurring radioactive material. This is potassium. How much potassium do you have in your body? The answer is a lot. Okay, it's not a big deal, but it's there, right? It's yeah. By the way, I'm going to try and keep my sources as far away from the detector as possible, so you can see me bouncing back and forth, because I'm trying not to pick up on the sources, right? Okay, here's another naturally occurring radioactive material. This is thorium. And thank goodness we have a geology department where I can go and say, hey, give me a piece of thorium rock, right? Okay, so they're all over the place. There's a whole bunch of other things that come from thorium and come from uranium that are in this naturally occurring radioactive material, but they're things that are generated from uranium and thorium. And so it's everywhere, okay? As a matter of fact, if you listen to the little clicks here, my sources are a long ways away. Still clicks, right? If I had a sensitive enough detector, we'd find that you have clicks coming from you. You have about like 130, 140 grams of radioactive potassium in you. And that amounts to about 1,500 little clicks per second if you could measure them for you, right? So you're radioactive. Did you know that? I didn't realize you were radioactive. Okay. Another source of radiation is what's called cosmic rays. These are sources from the sun and from other things way out in the space. And we won't talk much about cosmic rays, but they are quite interesting. And there's a lot of bits of physics there that we actually don't know much about because we're not sure 100% where some of these things come from. So it's pretty amazing. There's a lot of physics that we haven't learned about yet. We just teach you the stuff that we already think we know about. Okay, here we go. Oh, it's a natural phenomenon. There's no difference between the naturally occurring and the man-made stuff. There's no real difference in intensity. You can have naturally occurring materials that are quite intense and things that are man-made that are like, okay, we've had it, we've known it forever, okay? And our bodies are accustomed to it. That's what's important to recognize. Your body has been exposed to natural radiation forever, okay? As a matter of fact, if you go back in geological history, the level of ionizing radiation that our ancestors were exposed to hundreds of thousands of years ago is hundreds of times greater than what it is now, okay? And so it actually is getting less with time, not more, okay? And we'll talk about why that's so a little bit later. This is called background radiation, and that's what you're hearing over here. Click, 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 okay? It's just the stuff that's around us all the time. Where does it come from? Uranium and thorium and their daughter products, decay products, potassium in your body, cosmic rays, medical procedures. There's some other things going on there. Some places in the world are 10 times the average. There's a place in India and there's a place in Iran. This place in Iran is like crazy, right? In terms of how much more. But this is roughly what we are. Use like 0.4 for us in the US. And they're like 10. And guess what? They're fine. Okay. There's no indication that this background is a problem. Where does that background radiation come from? This is what you get. And you can look up calculators for this. I think they're a little worthless in the sense that it doesn't make any difference. You can calculate it if you want to. But notice that almost all of this is coming from natural sources. There's a few medical things that you do, a few artificial things. Okay, and we can talk more about that. Okay, so let's talk about our toy atom here. You've seen the toy atom before, right? It's got protons and neutrons in the nucleus and things zipping around. It's a toy atom because that's not how the real world works, but it's close enough for talking today. And so we're going to be talking about what's in the nucleus here, protons and neutrons. And you've heard the names before. We're going to try and illustrate, help you figure it out. But before we do, we have to have a little bit of notation here of what we're talking about. Okay. And one of the things we're going to talk about is that not all atoms are the same. Even atoms of the same thing like carbon, there's different versions of it. And I know many of you have heard that before from chemistry. course, if we look at the periodic table here, by the way, you can look at these references here if you need more information. Carbon's mass is about 12, but it's a little more than 12. Why is it a little bit more than 12? Because on average, there's some that are 12 and some that are 13, and some that are 14. Okay, so here's so we're just going to run through stuff that you probably know pretty well. It has an atomic number of 6, right? You've heard that one before, right? That means it has 6 protons. We're going to use the symbol Z to represent that atomic number. Okay, that gives you your chemical properties. Carbon has 3 naturally occurring isotopes. They're not radioactive. Okay, and we're going to use the A number to be what's called its mass number. Okay, that's the carbon 12, carbon 13, carbon 14, which you may have heard of before. So here are those 3 different isotopes that are commonly think. What's the difference between those isotopes? Well, they're still carbon. They still have protons, right? 6 protons. The difference is we add some additional mass in the form of neutrons. Okay. And so what does that mean? Carbon 12, that means it's 6 protons and 6 neutrons. And then we have carbon 13, which is, that's where I'm going home. It's too easy here. Okay, this number of neutrons is the, you sometimes use the number n, although we won't talk about the number of neutrons explicitly most of the time, simply because it's all just kind of lumped together and we don't separate them out. But okay, it's the sum of the, it's the difference between the mass number and the atomic number. By the way, for purposes of this class, we're not going to worry about fractional numbers. Okay, there are subtle differences between the mass of each of these isotopes, and they're important when it comes to physics because that's where the energy comes from, is the mass differential. But for talking purposes today and for the rest of the time we're here, we're just going to assume they're nice whole numbers because it's easier and it's good enough for what we're going to talk about. Okay, so most common one is 12. That's why the number in the mass number there is very close to 12. Okay, so a little more notation here. Different ways that it's written. 12 carbon, right? 12 for the number of protons and neutrons up at the top, right? 6 is for the number of protons in the bottom. And then you could write it also as, dash 12 dash, okay. How many neutrons? You guys can answer these questions. I think they're pretty straightforward. But notice that sometimes, since the carbon already tells us how many protons it has, sometimes they don't write that. I'm going to write that down every single time for my benefit, because past the first 10 or 12 elements in the periodic table, I don't remember any of them anymore. Okay, maybe that's you too, but I got the first 12, right? And after that, I don't really remember. So I'm going to write down the C12-6 business every single time because it's helpful to me. I'm not going to write down the number of neutrons, even though there's a way to do that. So there's the different notation that we might use, and we're going to do that. We already talked about that. Here's kind of a generic way of writing this. If I had an isotope, we'd say A was total protons and neutrons, total protons, right? Total number of neutrons. I am going to leave out the neutrons in there because, once again, it is redundant information and you can extract it. I just happen to not know the chemicals that well past 12. Okay. Okay. So let's do an example. This is potassium. You've got lots of potassium in your body, right? Its mass is 39 point change, right? Okay. How many protons does it have? Easy, right? Okay. How many neutrons does it have? Well, you don't know yet, do you? Because it depends on which of the isotopes you're paying attention to. So there's the 39, which is most of them, right? And then there's the 41, which is 6% or so, right? And then there's some 40, which is a very small fraction, but it's the one that has a nuclear component, because this is the one that's actually radioactive. This stuff has been around since the formation of the universe. I don't know exactly how it was created, but it's been around a long time, okay? It has a half-life, we'll talk about what that means, of, I think it's 14 billion years or something like that. So It's been around for about as long as the universe has been around. Yeah, yeah, what's your half-life? Okay. All right. You have, here's the number. It's suggested that you have about 4,400 decays in your body per second from the potassium that's in it. So, that's, so you're clicking away. This is, by the way, not an overly sensitive detector. If we put you in a very sensitive detector, there'd be a lot going on. Yes, please.
How does it have a 14 billion year half-life, but that many decay in the body?
There's a lot of atoms in the world. Okay. I know you haven't. Well, maybe you have, but we don't remember, right? I kind of think we have been, but that's a personal opinion. So yeah, that's a really interesting question. Think about it. You guys know about Avogadro's number, right? And you go carbon, 12, and there's 6.02 times 10 to the third atoms per molecule. That's a lot of atoms, isn't it? How many actual atoms are decaying? Well, it's 4,400 that are decaying compared to, right? So that's, it sounds like a lot, but it's, I'm sorry, it's nothing, right? Because you got 10 to the 23rd of them in every sample that you grab, right? Or more. So it's just really in the noise, okay, when it comes to how much is going on there. Okay, does that make sense? We already kind of guessed that that was the more massive one. Okay, so here's a chance to do a quick clicker question, see if you can answer this. These are going to be so easy for you. So do I do A? It's turned itself off.
Now they can do it.
Now you can do it. Okay. All right. This is all just basic add, subtract math for what we're doing here, but you didn't need to do it, so we're going to have a little quiz. Okay. 100 something know how to do it. This is less than Avogadro's number for the people. Okay. Okay, about ready to be done. Then A again. Okay. Oh. Okay. And then these are all the easy questions. Okay. So once again, the 137 that I'm indicating for cesium there is that total proton neutron count. Okay. So there you go. So let's see. There we go. Now you feel better about yourself, right? Okay. Once again, these are pretty straightforward. It's most of what we're going to do in this class, at least this first thing, is bookkeeping. Okay. When we come, so it's easy. Let's answer this question, but let's not do it as a quick clicker. Just do it for ourselves here. How are we going to determine this one? 137 again, 55 for the proton. What's the question that we're asking? And this is the problem. Sometimes people answer the wrong question, right? What's the question we're asking? I asked for how many neutrons. So how do we figure out neutrons? We're going to take the total protons and neutrons, total protons. Okay. Right? It's our neutrons. Sorry. That's wrong. That's wrong. Can you believe that? Yes, it is. This is what you get by sitting at your desk thinking you know what you're talking about. Okay, this is the correct answer for the wrong question, right? The question was, that's the number of protons, isn't it? Okay, that's why I didn't make you take that quiz, because I didn't want you to miss it. Okay, and then let's ask the question about number of protons. Okay, so then, okay, all right. Operator error. Okay. Here's the notation right there. Okay. It's a good thing you guys have never made a mistake. You know, that's the one nice thing about being older is that you've made a lot of mistakes. That way you recognize that you make a lot of mistakes. You guys are too young to recognize that you've made that many mistakes yet. Okay, we're going to talk about isotopes. And this chart where you can't read it, I promise we're going to talk about the details of it, but that represents the number of different isotopes that have been identified. And there's some 1,500 different isotopes that have been identified out there. And we're going to talk about a few of them there. The charts thing. We're going to zoom in here. Okay, so we're going to zoom in and take a look at that. Here's an example of one that we know. Here's carbon that we were talking about earlier. And then there's carbon 13. And then there's carbon 14. And then there are other carbon versions, right? Floating around there. Are we going to try and figure them all out? No. But it's like the periodic table, right? When you need to know it, you look it up. Okay? And I will never ask you to do something from memory out of here because nobody can memorize it all. So all these floating across here are carbons. This is the number of neutrons we add to it. And this is the number of protons we add in this chart. Does that make sense? Pretty straightforward. You just look it up. But notice there's a whole bunch of them. Some of these you may be familiar with. Here's hydrogen. How many different flavors of hydrogen are there? Well, there's one, the one you're most familiar with. Then there's what's called deuterium, has its own special name. And then there's this one called tritium. And then there's all these other ones out there that they've made before, but they don't last for any significant amount of time. And that's what the color coding tells you about. Okay. Most of the ones that are of interest to you are the ones in black. Okay, because those are the ones that are stable. Okay. And then if you go off of that line of stability there, one way or the other, and we're going to do a lot of that, that's when the interesting stuff happens when it comes to nuclear reactions. Okay. One step on either side, or maybe a couple of steps away. We're almost never going to deal with these out here, not because they aren't interesting, but because oftentimes they really don't last for more than a very small fraction. And only a nuclear physicist would get excited about those ones that last for like 10 millionths of a second or some other number. Okay, so for purposes of what we're talking about, we're going to stick with the ones that are close to the middle. Okay, so we're going to talk about different kinds of reactions. There are spontaneous reactions that take place, and there are induced reactions. The ones we're going to talk about first are the alpha, beta, gamma, and fission reactions, which are ones that happen spontaneously. Okay, they're not ones that I have to do anything to get them to happen. Okay, and then there's a whole class of ones that you can actually get to happen for you. And some of those that are induced are super important for medical and other purposes. We'll actually set up something to become radioactive that wasn't before. That's an induced reaction. And so we're gonna do a whole bunch of different examples here. Okay, so here are the four primary types of spontaneous nuclear stuff. You've heard of these before, so I'm not going to belabor them too much in this slide. We're going to go through them. By the way, some of these slides are here for completeness, not because you need to read them or write them down so that you can have the references. Okay, so let's talk about the first one called an alpha decay. And that we know now is a energetic helium nucleus. Okay, it doesn't have its electrons because it's too energetic. It's an ionizing particle, right? Eventually, it will grab some electrons and it'll become helium. Okay, as you can guess from your chemistry knowledge, so there's our symbol for it, right? It's each proton is about 1,000 times the mass of an electron. And so there's 2 protons and 2 neutrons in this little thing called alpha. So there it is, about 4,000. Very, very massive. What does that mean? That means that whenever it collides with something being very massive, it's going to transfer its energy to the neighboring stuff very quickly. That's what we call a high linear energy transfer. It's like a big, huge truck smashing into a little tiny car, right? Lots of energy transfer, okay? What's interesting, though, is it's also transfers that energy very quickly, so it actually doesn't go very far, Okay, and I'll show you that in just a second. With real data. I like real data. Okay. All right, so let's take an example of alpha decay. The one we're going to show you here, and I've got a sample of it over here. It's called americium 241. There's our notation for it. Okay, 95 protons, right? I'll include that one because I don't remember americium has 295 because I don't know, even though I talk about it all the time. It's going to go through a decay process that looks something like this. Americium, and it's going to become neptunium. And it's going to give off an alpha particle. And here's where we get to do a little bit of adding and subtracting, right? The total number of nuclear particles, nucleons as they're called, is 241. So that when you get over to the other side, you better have 241. 237 plus 4. You can do the math, right? Not too hard, okay? And you just have to add them up. You have to add up in terms of the number of protons. We started out with 95. 3 of them end up in the Neptunian. Okay, that one, right? The N one, okay? And then 2 of them end up in the helium, right? So pretty straightforward, bit of algebra. Atomic number. Okay. Atomic number of protons goes down by 2. I got to make sure I didn't do the wrong thing. Checking my own slides here. Okay, mass number by 4. So far so good. None of this stuff is overly difficult. Let's look at how that would work on our little chart right there. The example I've chosen here is tungsten. Tungsten 180 here. Tungsten has 74 protons. There's my reaction there. It's going to kick off a helium nucleum, and then it's going to nucleus, and then it's going to create hafnium here. And did we do the math correctly? 180, 180, right? 74, 2, and 74, right? Total. Here's what we do on the chart. Sorry about that. Here's the tungsten, 180. It drops down along a line like that. So it's dropping 2 of these and 2 that direction. Okay, and that's how you find the answer. Okay. Just to point out some things here, there is some useful information in this table. Of course, the 176, of course, is the total number of nucleons. Here's the Z number, which is your total number of protons. And here's the number of neutrons. So they gave you all the information you need right in the chart. By the way, this is off of the International Atomic Energy Agency's website, and you can go there yourself. And these other fun numbers right here, you don't need to worry that much about. This is actually the half-life, which is a number we'll talk about. This number right here, not going to ever worry about because it's complicated. Okay. And for what we're talking about. So we're basically counting, right? Stepping down, stepping over. Easy enough? Okay. All right, so now you get to do a clicker question. These are also easy for you. But we ought to do one, right? So that you feel like you. By the way, your homework is going to be problems like this, right? Can you figure out what you get when you're done? Okay, so do you know how to figure this one out? They are. Yeah. You guys are just like the detector there, clicking away. Okay, is that good? I don't know what's the right number. Anybody still need to answer? Okay, we're going to call it good with you. I think I pushed the wrong button. Oh, you all know that it's C? Let's see. How do we know? C is 132. Better add up to 4 plus 128. Does that add up to 132? And we better check our proton number. 90 plus it is 2 plus 88. Oh, I think you're probably right. Okay. Let's see. Who's in charge around here? I don't know who did that. C's the right number, isn't it? I know what the problem is. I'm blaming it on somebody else. When I put these little circles around there and then you rescale things, it's not on the right spot. But that's not really a good excuse. It's probably true, but it's not a good excuse. Okay. So, well, what's nice is the student version of this doesn't have the wrong answer in circles, so you're good. Okay, the one that Greg said. Okay, the next one is called beta decay, and there's two flavors of beta decay. It's actually more than that. This one's going to be called beta negative or beta minus, and it's going to kick out what we call an electron. And so there's your fun little toy model, toy atom, toy nucleus, kicking off a little electron. There's the notation that is sometimes used, an E with a minus sign. See that in chemistry quite a bit. In our case, we're going to probably use this B or beta minus notation as well. Okay, so my example here is cesium-137. It's going to go from cesium to barium. Okay, notice that the total protons and neutrons stays the same. Okay, and what we ended up with is changing the number of protons. Of course, that makes sense. We change the number of protons. It's no longer cesium anymore. It's now barium. Okay, now think about it for just 1 second. If I have more protons than I had before, but I have the same number of total particles, I must have converted something from something else. What might I have converted from one thing to the other? I converted, what else do I have in the nucleus? I have neutrons, right? So I must have converted a neutron into something. What did I convert the neutron to? I converted a neutron into a proton. Total number of protons and neutrons didn't change, but one gets converted. So we basically add one more proton and we kick off an electron. Just for purposes of remembering that in chemistry and in physics, we want charge to be conserved, which means that we kicked off an electron, which means we increased the number of positive charges in the nucleus by 1, right? Okay, so nice conservation rules, conservation of mass, conservation of electric charge. Now, I'm gonna include this in our discussion here later, but remember, there's this thing called gamma, and that's gamma rays, and we're going to talk about that in more detail later. But it turns out that almost always in one of these reactions, you get some energy left over, and it's got to go in some form, and it usually gets kicked out in the form of a gamma ray. Okay, so almost always there's a gamma ray associated with everything we talk about. Okay, and the beta particles are quite easily stopped. They have a relatively low energy transfer, but they're not very big, right? So for talking, well, we'll give some examples. Okay, so you can stop beta radiation quite easily with a few sheets of aluminum material, and we'll show you some examples of that. It's difficult. 2 buttons, pushers here. He's the master. He can do 2 buttons there. Okay, here's an example. This is one you hear about quite often, actually. Carbon-14 is a radioactive isotope, and it is one that we use to do a lot of really interesting physics with, and used in geology and archaeology. We're going to take, and we're going to convert carbon-14 into nitrogen-14. Remember, inside of that, one of the neutrons gets converted to a proton, kicking out a beta particle and some gamma energy. This is the reaction there. And what does it look like on our chart? We started at carbon-14 and we cruised this direction, right? Okay, so we ended up with nitrogen. Of course, the math all adds up, right? Here's the conversion. We went from, let's see, I always have trouble with math. We had 14 total nuclear particles, right? I increased the number of protons, which means that I decreased the number of neutrons. So it's all right there in the chart, and it's super easy to do, okay? It's just bookkeeping, you know. You didn't know that you're gonna become bookkeepers, but a good portion of physics and chemistry, at least like this, is bookkeeping. Okay, so let's see if you can do a clicker question. Are you ready? Do you know beta decay? I think. All right, can you figure out? Okay, so this reaction is indium. And I don't know who the operator of this computer is. It's not 16, it's 116, right? Somebody keeps typing poorly. I do have the correct notation right here. And this is why I like this notation better, because I don't remember what the notation is for indium. I don't remember. Okay, you ready? You get it all figured out? Okay, I end it with A, right? And then I show you with B. Is that correct? Did I get it wrong? That is correct. The question I don't know is, let's see. Did I mark it correctly? Okay. You know, one of the really nice things about this job is you can't fire me. And you can do rate my teacher all day long and nobody's gonna read it. Because nobody knows who I am. It's great. Okay. All right. Okay, we're gonna do another kind of beta decay. It's called beta plus. And it's actually quite rare. And yet it has some very important applications in the medical field. So we want to mention it. And it's gonna look kind of like beta decay in the sense that it is going to kick out something that looks kind of like an electron, except for it's not an electron. It's called a positron. Okay. And it's going to kick that thing out. And so we're going to do kind of the reverse process. We're going to go from, so before we converted a neutron into a proton, this time we're going to convert a proton into a neutron. Okay, and we're going to kick out something. This time we're going to kick out a positively charged particle that has a mass just like an electron. Okay, and so in our little chart here, we're going to cruise this direction. Okay, and this is actually this is a compound that this is a nucleus. This is an isotope that is commonly put into different chemical compounds, and they inject it into you, and then they can make images with it. Okay, so that's why I included it here. The electron and the positron will always collide with each other and annihilate and give off a very characteristic set of gamma rays, and that's how you can detect it. Okay, and you may have heard the term PET scan, positron emission tomography. And that's what this is about, right? Okay, and we'll try and talk some more about that in a couple of days. Okay, let's see. Okay, there is a thing called electron capture. I'm only just going to say that it mention that it exists simply for the fact that it'll sometimes people will talk about it. Okay, do you need to know anything about it? It acts like a beta. Sorry. It acts like a beta positive in terms of the numbers of protons and electron shift. But what actually is happening is it's stealing an electron inside the electron shells into the nucleus, right? So it's a little bit different. You're capturing an electron from the electron shell, and the radiation is actually due to the electrons in that vacant spot cascading back down to fill. Thing. Once again, I'm not trying to mess with your heads too much. Just for completeness, it's there. Okay, now let's start talking about energy a little bit. Hopefully you've heard of this before. Did you guys do electron volts in anything before?
I have not.
Okay. Well, it turns out that when you guys were studying electricity and magnetism, you would talk about taking a charged particle in an electric field, and you would say, move it from one place to the other. And you'd say, well, if I went from 0 to 100 volts higher, I'd given it some energy, hadn't I? So a convenient unit of energy on the atomic and nuclear scale is to actually talk about how much energy you gave to an electric charge, a fundamental charge, when you moved it through a particular voltage. So if I moved it from 0 to a higher voltage of 100, then I gave that elementary charge 100 electron volts of energy. Okay, now it's a bizarre sounding unit, but it's very convenient, and you will find that when we talk about energy in nuclear, it's all expressed that way. Okay, now it is a very small amount of energy. Okay, you can look that up whenever you need to make the conversion, and we will use that to convert, because in ordinary situations you use energy units like joules, right? And if we're going to talk about how much energy a nuclear reaction deposits in the tissue of a body, then we're going to need to do it in terms of units that we're familiar with for bodies, right? Like kilograms and joules of energy and things like that. But at the atomic level, we're going to be talking in terms of electron volts. So we have to be able to go back and forth. It's a pretty straightforward calculation, just a unit conversion. But it is important to realize that nuclear energies are thousands, if not millions, of these electron volts, whereas a typical chemical reaction is on the order of tens of electron volts. Okay, so it's very important to recognize when we're talking about energy, nuclear reactions have thousands, if not millions of times more energy per reaction than you do in a chemical reaction. Okay, so it's a lot of energy. And so despite the fact that it's not very much energy total, because electron volts is a small unit, the energy for that particular event is oftentimes very large, right? Energy per the mass that you're dealing with. So big deal. Okay. So now we're going to talk about shielding. The reason I want to talk about shielding here is because it's a kind of a fun way to detect what kind of radiation we're looking at here. Okay, we already alluded to this, that alpha particles and gamma get blocked fairly easily. Alpha and betas. We already alluded to the fact that the alpha particles are stopped fairly easily. Beta is stopped by a few sheets of aluminum. Gammas, they go through quite easily. We're going to talk about neutrons just in passing today, but they actually turn out not to be easily stopped at all because they don't have any electric charge, so they tend to zip through things. They do get stopped quite easily by things that have lots of protons in them. Turns out that neutrons and protons have about the same amount of mass, so they stop quite easily. Okay, so we're going to talk about these. I won't show you any neutron reactions because, one, they're kind of dangerous, and they're also kind of hard for me to set up here. Well, let's talk about some shielding. Oh, sorry, wrong button. Okay, here we go. Let's do it. Let's actually do real interactions here to give you a chance for some of you who decided a nap is more interesting on the boring stuff. Come back. Okay, this is the guts of a smoke detector. Okay, it has in it a little tiny drop of a isotope called americium 241, and I already showed you the reaction of, oh, I've got it up there again. Okay, so here it is. So there it is. There's the smoke detector. But watch what happens very quickly here. What would that suggest to you about what alpha particles can do in air? Can they travel very far? I mean, look at how that signal drops off. Even in air, the alpha particles transfer their energy so quickly that they can't actually go very far. And I was supposed to bring you a piece of paper to show you this, but guess what? Our friend Greg has left us a piece of paper. Okay, so here we go. Nice strong signal. Sheet of paper, right? So what do we know about alpha particles? Quite easily stopped. Now they do transfer quite a bit of energy, when they collide with it, but they don't go very far. Okay, does that make sense? And so some people might be concerned about a smoke detector. Isn't that going to kill you, right? Because it's in your house, right? And the answer is, well, guess what? One, it's not very close to you. Two, it doesn't travel very through air, and this is actually covered by something. So the reality is, the alpha particles from this can pretty much never do anything to you. Okay. As a matter of fact, alpha particles are so easily stopped that the only real risk to an alpha emitter is if you were to eat it. Okay. And so, or breathe it in or something like that. So wouldn't recommend it. You're not to eat this. Okay. But it's not that tasty anyway, so I'm not sure why you would want to. Okay. Now, there is some other energy in this alpha decay here. Okay, you're still hearing some background, right? There's still something going on there. What's left over if I take my piece of paper and I block it? Well, still something is getting through. What is it that's getting through? And so what we told you before is that most times when there's a reaction, there's some of this extra energy, these gamma energy. Okay, so that's typically what you're getting through once you've blocked it with a sheet of paper. And I've actually done some data here for you. Here's some data I took. Part of the problem with taking nuclear data is it takes a long time to get good quality data. So we can't do that in front of you very well. But you can see my unshielded there. I'm getting around 500 counts per minute probably. And then I put a piece of tissue paper in front of it. And you know, there's 2 sheets of paper. You can see I knocked the signal down by about half, didn't I? Just by sticking a piece of paper in front of it. And then notice what happens is I add pieces of aluminum, it kind of tapers off. So what am I using? What am I blocking with the aluminum? Well, I'm blocking those extra bits of radiation, gamma rays, typically. And this is kind of interesting here. Notice that when I added a little piece of lead here, I've added some pieces of lead. What's that? What am I at? I put it in for reference. I have background right there. What stopped everything? And that's a few millimeters of lead. Okay, stopped everything. So not very penetrating radiation. So once again, don't eat it. You're not allowed to eat it. Okay, but the risks, as long as you don't get it inside your body, are pretty minimal. Okay. All right, let's see. What do we have next here? Found the button here. So so you can tell quite a bit about what the kind of radiation is there by just looking at how the signal drops off with different shielding. Okay, let's talk about a beta shielding. I've got cesium-137 as my example here. And I just used some aluminum, and I just kept adding some aluminum here. And notice what happened is, there's my signal. Let's get out the cesium-137. That was more fun to actually do demo, right? And then just talk about it. There's my cesium-137. Throw a few sheets of aluminum on it. That's you know, it's like a millimeters of aluminum. What happened to the signal? Dropped off very quickly, didn't it? There's about 5 millimeters of aluminum. Okay, so now I've got about 10 millimeters of aluminum there. So we're not zero yet. What does that say? I blocked most of everything, but I still have some coming through. What did I block? I blocked the betas. What do I have coming through? This is the answer you're always going to say. What's left? Was the gammas, right? Okay. And there you can see them right there. After I put the aluminum in there, I still see some gammas there. And I don't block those gammas very easily, although I can. If I go and throw a little bit of lead in front of it, we're basically back down to background, right? So pretty easy to block the betas, right? little bit of aluminum. What about your skin? Would your skin block the alphas pretty well? The betas, mostly. Your real risk of a beta emitter, once again, if you don't eat it, would be, you know, injury to your skin. Fortunately, you're never gonna actually be exposed to very many of these things. Okay, so there's an example. We do another beta emitter. One of my favorite beta emitters. Why do I like it so much? Okay, this is strontium 990. And I'm gonna throw a little bit of aluminum in front of it. That sounds pretty close to background, doesn't it? Didn't take me very much to block that, just a few sheets of aluminum. There's nothing left. As a matter of fact, I can actually say, well, suppose there were some gammas there. I should make that signal go smaller, and I can put aluminum, I can put some lead in there, and it's pretty much background. So what does that tell me about the strontium signal? It's a beta emitter, and they're pretty energetic betas, but pretty much no gammas. So after a few millimeters of aluminum, I'm done, right? So very, very easy to tell what you've got going on here. By the way, what have we just discovered about shielding? What's one of the best ways to reduce your exposure to something? Well, you can put lead in front of it, but what am I doing over here? I just put it away from you, right? The simplest way to reduce your exposure to anything, whether that's chemical or whatever, is just not have it around, okay? That's pretty straightforward, isn't it? Okay, I want to show you, let's see. Sorry, don't want to get ahead of my slides here. Okay, so let's talk about electromagnetic radiation. You've done this before. I guess I have this one over here. I turn them that way. You're familiar with X-rays, gamma rays. You're familiar with all the spectrum of the light there. We're talking about stuff that's up in this energy level here. It's electromagnetic radiation. Why did I bring that up? Because I want to talk about gamma decay. Remember, gamma is that extra energy that's oftentimes left over when you have something taking place. And so I want to show you an example of a gamma emitter, which is actually quite relevant to lots of medical and other applications. They use this cobalt-60 for zapping tumors and so forth, right? Once again, we're talking about big sources. This is tiny. And so here's cobalt-60. I've actually put in the relative energies. Those beta particles are actually very weak, but that gamma energy is very large. And throw a little bit of aluminum on there, we'd expect that if most of the energy is coming from betas, I would block it. Did you hear much difference there? So it's kind of like, oh, where's the energy hanging out? Well, probably not in betas. What if I put some lead in front of there? Sure, the signal's dropping off, right? But you still see quite a significant thing. What does that tell you about the energy that's being released from this cobalt-60? Mostly gammas, right? How easy is it to shield gammas compared to alphas and betas? Much more difficult. Does that run a much greater harm to you externally? Sure. In a medical application, they literally will put this whole thing in a big container like this, and they'll have a little place going through it like this, and they can rotate the door to let the beam of gamma ray come through it. And but it's this big, huge block of stuff. By the way, when I'm talking about a medical source of cobalt-60, it's probably on the order of 1,000 or more times stronger than this little clicky thing here that I have here. This one is 1 microcurie, which we'll talk about what that means. And some of these sources are bigger than that. Some of them are several curies. So it's enough to fry you pretty good, right? But that's the whole point, is they're gonna try and zap, say, a cancer cell with that high intensity beam, but they're gonna stick it in a very nice shielded thing, so it's blocked everywhere except for the little beam that you want, okay? Oh, we jumped ahead. Okay. I'm glad somebody's pushing the button, okay? So just a real quick summary about the thing, and I actually included some energies in here. The americium is the alpha emitter, 5 million electron volts, about 5.5 million electrons. It's a lot of energy, turns out, okay? But the energy is dissipated very quickly, which means it doesn't go very far. So don't eat it, okay? The gamma rays associated with the americium, not very strong, only about 50,000 versus this cesium. Betas aren't particularly energetic, but look at those gammas, right? Lots of energy, and we saw that in our chart. Okay, the strontium didn't have hardly any gamma, and then our cobalt had quite a bit of gamma energy. And so one last shot to summarize all of that what we just said. Okay, alphas have easily stopped. They have a low energy set of gammas. You can see that right there. Not a lot of energy. Didn't take very much to block the gammas. Let's see. My next example was cesium. Had low energy betas and medium sized gammas. This one over here had higher energy, medium energy betas. That is more than this one over here. But once I'm done blocking, there's nothing left. And then this is my cobalt 60. Low energy betas, but lots of energy associated with the gammas. Okay, so that's what you got to pay attention to. It's not just, oh, it's radioactive, right? That doesn't tell you hardly anything. As a matter of fact, one of the things that's a real problem with this Geiger counter here that people hear, you hearing this thing clicking away, or, you know, and I even get crazy and go, here's a sample. And the people on the front row start going, oh, what? It tells you 0 about the risk here. Oh, a little bit, because you know, if it's more clicks, then yeah, more things are happening, but it doesn't tell you anything about how much energy is being released per event. So the Geiger counter is kind of a worthless tool when it comes to measuring the potential harm associated with the nuclear radiation. By the way, why am I using the Geiger counter? Well, I have one, okay? That's why we're using it, because it's one you could actually get a hold of and so forth. But in a real case where we wanted to know the details of how much energy is being released and how much potential harm that could be, we need a better detector. And we need something that can actually tell us how much energy is happening per event. The other thing that's important to note as well is nuclear detectors can be extremely sensitive. An appropriate nuclear detector can detect single nuclear events, which is quite amazing. You were asking earlier about, isn't that a lot? And the answer is no, because there's 10 to the 23rd of them, except we can detect individual events with the right kind of detector. So sometimes people get the false assumption that because I can detect it, it's somehow a problem, right? And that isn't by any means the truth. Just because you can detect it may not be anything. You know, in chemical things, you might be able to detect things down to the parts per billion range in chemical thing. You can literally detect nuclear events down to the 23rd level, right? Avogadro's number. So you can detect very, very precisely. Oftentimes the noise of what's going on in the background is a bigger signal than the thing that you could potentially detect. So we oftentimes ignore them when they get that small. Okay, let's see where we're at next here. Oh, let's talk about neutrons for a second. Neutrons are really interesting, and we won't talk about them very much. I don't have a good detector for neutrons. But this is a picture that my friend John Ellsworth, who works here in the physics department and does a lot of cool nuclear stuff, shared with me. This is a rose that is sitting inside of a cylindrical container made of lead. And neutrons are streaming through this lead container. What do you think you can learn about how neutrons behave? Does lead stop neutrons very well? Goes straight through. It's kind of interesting. But what is stopping the neutron? You're seeing a neutron shadow from what? The rose. What is the rose made of? It's made of carbon, isn't it? And hydrogen. And it turns out that neutrons have a mass that's about the size of hydrogen. So things that have lots of hydrogen stop neutrons pretty well. So if you wanted to shield yourself from a neutron source, go jump in a pool. Okay? It's great shielding for neutrons. Now, it's also a bit of a problem because neutrons don't get stopped by other things, and they would get stopped by you. So unfortunately, if you were in a high neutron environment, you could get absorbed in you, right? Because you've got lots of protons in you, and so you would be actually a reasonably good neutron absorber. Fortunately, you don't actually have to worry about neutrons too much because there aren't that many neutrons just floating around in space, you know. Quite honestly, even in a medical application, the number of neutrons that are available is pretty close to zero. Okay. All right. So neutrons are cool. And we are getting close to the end here. I have some more things to talk to you about. Summary of what we talked about so far. Okay. Let's just mention a couple of things. Fission is another spontaneous process as well as an induced process. When we were playing around with the radioactive rocks like the uranium, it's actually fissioning on its own. Nothing caused it to do it, it's just decaying. And it's kicking off some neutrons and some protons and electrons and a bunch of stuff, right? So that's a spontaneous process. We also can induce fission, which we'll talk about in more detail later. And we can hit it with a neutron, and that can cause it to split into some pieces. And here's an example of uranium-235 being hit with a neutron. The accounting is just a little bit more complicated because there's more places to do the accounting, but 235 plus 1 is 36. Over on this side, I've got 240 plus 94 plus 2 1s, right? So it better add up to 235, although my track record of doing arithmetic has been pretty poor today. And you just add them up, okay? One of the challenging things about nuclear fission, it turns out, is it's hard to predict how big the pieces are, because the pieces can be in all kinds of different sizes. And that's one of the complexities associated with nuclear reactors that produce energy. Okay. Quick little thing we'll just throw in at the end here. Oftentimes things that are radioactive, that was useful, are radioactive, also have decay products that also can be radioactive. And so we oftentimes get what we call a decay chain. Here's an example where thorium-232 actually decays through a whole bunch series of steps, and it can take a long time to do that, and it ends up being lead. Okay, so it's not uncommon for something, when it is radioactive, decays into something else that's radioactive, and it'll go through multiple steps holding the decay chain. Sometimes it'll go through one step and then it'll be stable and everything will be done. But for the naturally occurring ones, it's actually quite common. And it turns out that every one of these steps along the way is also radioactive. And so those daughter products, those radioactive daughter products, contribute to the background radiation as well. Okay, and that's good. Okay, I think we're going to be done. I think we're going to quit here. We're going to talk about the mathematics of decay. Next time we meet, we're going to talk about things like half-life, and then we're going to try and apply that to what kind of dose that might be if we're going to apply it to a medical situation. So thank you for your patience with me. Have a good day.